What are the forces, challenges, and ideas that define the 21st century? Conversations to understand the greatest figures and stories of today to create a better tomorrow. This is the 21st Talks podcast. Hey everybody, and welcome to today's episode of the 21st Talks podcast with me, Coleman Snell. Today is October 26, 2020. Today's guest is Elliot Lehrer, who is a senior at Brown University studying physics. He's also a good friend of mine and has contributed to some blog posts on my website, as well as with a couple of the interviews so far for this podcast. So this interview is about a month old. It was when the podcast was known under a different title and before the rebranding occurred, but I didn't want to hold back from you guys. I didn't want to keep this podcast episode and this wonderful conversation genuinely on my computer hard drive until the end of time. I wanted to get it out there for you guys because it's a fun conversation, and really it corrected a lot of my misconceptions I had about quantum mechanics. Circles in a way that kind of bastardizes the principles of it a little bit. Elliot and I were on a crusade to fix that today, in whatever small part we could. But nonetheless, it's a really, really good time. So I'm glad that you guys are here. Grab a big ol' can of popcorn. I don't know why you're eating popcorn out of a can. Strange choice, but I'll allow it. And sit back, relax, and get that pen and paper out, because there is going to be a thorough exam after this. So you want to make sure to get high marks. Otherwise, your father and I are going to be very, very disappointed in you. This is episode 5 of the 21st Talks podcast with me, Coleman Snell, and my conversation with Elliot Lehrer, correcting quantum mistakes. I hope you guys enjoy this episode, and please don't forget to leave a like, rating, or subscribe on whatever platform you're listening to this to, especially on Spotify and Apple Podcasts. The ratings really, really go to help this podcast grow, and the feedback is incredibly critical at this early stage. So thank you guys very, very much, and I'll see you guys right back here next week. So hi, Elliot. How's it going?
Hi, going well. Excited to be here.
You're not exactly new to the podcast. You're on last week's episode and did a really fantastic job helping us prepare for it and actually get ready.
Yeah, thank you. This has been a really interesting project so far.
Well, you are currently working on an article for the website about this topic, quantum mechanics. So we figured we would talk it out and hash out some more ideas and sort of go more in depth in places that the article, is a little bit outside the article's focus. So I think that, I know I'm really stoked to have you on today, because it'll be a really fun talk. So I guess the first question is, all right, so the first question is, who are you and why are you interested in quantum mechanics?
Sure. So I'm Elliot Lehrer. I'm a rising senior at Brown University. I'm triple concentrating in math, physics, and philosophy. I'm interested in quantum mechanics mainly because I'm human. I think everyone should be interested in quantum mechanics. It's probably, I'm sure you're about to ask me this, but I think it's one of the most interesting phenomena that's 100 years ago, we just discovered this theory about the way the universe may or may not work, and still we're confused on what it means, and we're still asking questions, and still as physicists and as a society we're trying to incorporate all of its ideas into how we think about the world. So it's really impossible not to be interested in quantum mechanics is what I would say.
Well, I feel like the issue is of interviewing someone who you have already worked with is they can predict your questions, but that's also an advantage because that means I have to talk less. So that's perfect. But I think my next question is, what's at stake? Why is quantum mechanics, beyond why it's interesting, why is it important?
Yeah, I mean, quantum mechanics, really at the heart of quantum mechanics is questions such as, is the universe fundamentally random? Or is there a deterministic way to go from one process to the next? Do things have properties? Are they there when we're not observing them? There's this famous quote, is the moon there when we're not looking? And quantum mechanics is actually at the heart of that question. because some particles displayed behaviors that makes it not so clear whether or not the particles are even there, or how they behave when there aren't measurements going on. So we'll get into this later, but there's also things such as teleportation involved in quantum mechanics. There's quantum cloning. There's a bunch of there's a bunch of really fun just ideas, just general ideas about the universe that whose heart is built into quantum mechanics.
It seems like quantum mechanics is probably really, really involved in inspiring science fiction writers. Then, in that case, which I think, and we'll talk a little bit more about the pop culture aspect of it and interpretations a little bit later after actually diving into the specific interpretations from physicists. But yeah, I can already see the connections forming between specifically the quantum cloning. I feel like that's just a go-to phrase for science fiction writers is let's just add quantum to this. Let's see how that influences the reader's interpretations and stuff. But actually getting into the research you've been doing, there are four, maybe five approaches we're going to talk about today. And the one that like kind of struck me the most when I was doing some of the preliminary research for this episode, is the many worlds approach. Can you tell us a little bit about that and explain it?
For sure. So the many worlds interpretation of quantum mechanics was created in the late 1950s, so around 20 to 30 years after quantum mechanics itself was discovered. It created by this guy named Everett, who actually there's a funny story about him. This was his PhD thesis. He just created this entire interpretation of quantum mechanics as his PhD thesis at Princeton, and then proceeded to not do physics again. He just dropped out. He started doing like weapons and defense research for the federal government, and so never actually got to promote his idea. Uh,
Wait, so was it not as quickly sort of did it not have as much standing in physics early on in its development then, in the
yeah,
sense
no,
of like after it was created, because it was just some random PhD kid at
no,
Princeton doing
exactly. It had actually none at all. It took decades before anyone like noticed his ideas or took them seriously. And obviously nowadays, probably a lot of people have heard of the many worlds interpretation. This notion of there being parallel universes where things are slightly different does actually come from this very real possibility of how physics works. But yeah, for a long time, it wasn't even considered.
So when I was doing some of the reading before, it seemed like one of the advantages of this approach. And when was it created? Was it like the 50s or 60s
Yeah,
or?
it was late 50s.
Okay, so it seems like one of the advantages is it takes away the need for randomness, and also like action at a distance. Can you explain what when quantum mechanic interested individuals say randomness and also action at a distance, what do both of those terms mean?
Sure. So I think to talk about randomness, what we really need to talk about is superposition.
Hmm.
And so what's going on in superposition? It's this different type of state, you could call it, in quantum mechanics. The idea is, uh, given any two quantum mechanical states, you're allowed to combine them together. This is like just something that comes out of the math of quantum mechanics. If you have, like, say, a particle right here, and that same particle can be over here, like there is a new state called the superposition of being here and being here that this particle can then be in. And obviously, when we go around like walking outside, we don't see things in two places at once. And so this is like a big question of, oh, what does it actually mean for a particle to be in a superposition of two different states, or they can be in a superposition of, having like spin up or spin down, for example. This is a common microscopic property of the electron.
Mm.
Um, and the way that we sort of don't run into issues, because even electrons we sort of don't quote unquote see in two places at once, because when we interact with them, they're only in one place. So when we measure them, measure is a loaded term, but when we measure them, they're only in one place at once. So somehow the universe decides, going from this superposition of being on my left and being on my right, it it collapses into either being on my left or being on my right. And some interpretations of quantum mechanics just say, well, we don't really know how that works. And by some, I mean the Copenhagen interpretation, which we'll
Yeah.
get to. We don't really know how that works. Like it's just random. Like there's just this random It's this unexplained random process of going from this superposition of a state we don't really understand well into a normal sort of state where it's just, say, the particles on my left. And
Mm.
so what the many worlds interpretation does is it totally gets rid of that randomness because instead of every time we have a superposition, you measure it and it has to randomly choose which one you're going to end up in, it actually says both happen, which is this radical idea. So it's literally saying there's both the electron to my left and there's the electron to my right. But we don't see two electrons. So actually that's where the many worlds come in, is that there's one world in which I'm here, I'm observing the electron, and it's to my right. And then there's a sort of parallel world in which there's a copy of me, and I observe the electron to my left. And so you get to avoid randomness, which is very nice. So everything in the universe is deterministic.
Mm.
But along with this removal of randomness, you've brought with it like an infinite number of parallel worlds, each of a new one coming every single time you would have a measurement. Because every movement from this sort of superposition of states into these normal states
Mhm.
creates two new possibilities for how it could have collapsed.
And it seems like this approach is one of the most in line when it comes to the sort of the standard sort of vocab and culture of what is like Western science, in the sense of this sort of Newtonian notion of determinism that's now really hard set and sort of built into um, a lot of philosophers, this law as well, law of materialists, like view of the world and view of individuals and view of free will even. So it has a much larger consistency with what is, propagating common within science at large and within sort of like atheist culture at large and other aspects. Do you think that's one of the reasons why it catches on, or is it one of the more popular approaches?
I mean, I think that's definitely a reason it's in consideration.
Hmm.
Having everything be deterministic is really nice. Einstein
Yeah.
himself had a really famous quote: "God does not play dice with the universe," exactly referring to this idea that, well, how things work shouldn't just be this random process we shouldn't understand.
Mm.
Uh, and it's just really useful to be able, like, the project of physics is so much easier if we know that things happen exactly for a reason and it's not
Mm.
random. And life is easier if we can actually say, okay, well, this wasn't just some random process. Like, there's a causal chain that led up to it, and this is what was going to happen anyway. So it's a very comforting idea, and certainly something that we interact with in our daily life.
Mhm.
Uh, and so I think in that sense, yeah, definitely one of its major contributions for why it's caught on.
Well, it seems like the sort of chaos of the universe, right? Which like all of us as individuals and also as like thinkers and societies have to kind of contend with and try to make and construct some sort of order out of. That order creation is one of the tasks of science, right? It's how do we create ideas and observe the world in such a way that allows us to create theorems and then discover laws about how things operate to give us more utility over the entire thing, right? Which is the involvement with technology and science. That is, at least in my opinion, solid proof that there is utility in knowledge, at least certain kinds of knowledge. And it seems like quantum mechanics, the issue there is we're looking at the most fundamental things, the most fundamental particles in the world. Are in existence. And it doesn't seem like it is predictable, right? It's
Right.
like it's essentially it's akin to us being hunter gatherers once again, looking up at lightning and not exactly knowing how it works. And it's really easy, at least I'm sure it is for a lot of religious folks, to kind of just throw up their hands and say, well, it's God or it's another force. And then scientists across the board still want the predictability. They still want the ability to actually say, no, it's deterministic. It fits this larger worldview that we have sort of crafted, and that our like career as well as culture in a lot of ways has kind of informed our approaches. So it makes a lot of sense that it, is one of the more embodied ones. And um, could you explain the oh sorry existence in many worlds more in, oh yeah um could you explain how it compares to Bell's theorem a little bit more?
Yeah, so Bell's
Okay.
theorem is this result from 1964 by Bell, like this famous mathematician and physicist,
Hmm.
that ended up saying that what's called a local hidden variable theory is incompatible with quantum mechanics. just the basic math, the basic outcomes of quantum mechanics don't allow quantum mechanics to be explained by local hidden variables. And what local hidden variables are essentially uh, pieces of truth about what's going on at every point in the universe, sort of
Hmm.
set by that point in the universe. So a local hidden variable about an electron, for example, would be, well, is it right here or is it right here? And if there's just a variable that determines that at all points in time, that's a local hidden variable describing the position of the electron. And so Bell's theorem says that that's not possible to have. So that's
Mm.
outlawed. That's done. We cannot have an interpretation of quantum mechanics that actually just says, okay, well, for every single electron going on, there just is a matter of fact determined by that electron itself um, of uh, yeah of its position of its momentum and
What's when was Bell's theorem created? Was it? I assume it was later than the many worlds approach.
well, yeah, so Bell's theorem was created in 1964.
Okay.
um, and but what's interesting with the many worlds approach is uh, it doesn't violate this. It doesn't violate Bell's theorem. And looking at how each of the interpretations we'll talk about doesn't violate Bell's theorem is pretty interesting because there's like a common misconception about Bell's theorem says that you can't have just a local, you can't have hidden variables. But actually, you can have hidden variables as long as it's sort of determined by the universe itself. You just can't have local hidden variables. So that's an important distinction to me. It probably sounds pretty unexciting to the vast majority of people. Uh, but yeah, the many worlds interpretation does end up abiding by Bell's theorem.
And I guess for the two of them, just to further delineate the difference between the two, um, when it comes to the many worlds approach, right? Like I was thinking about it a little bit earlier, and it seems like the many worlds approach is not similar to another like very popular sort of pop sciencey idea right now, and that's sort of the idea of living in a simulation, right? The classic like Elon Musk or um, there's tons of philosophers of mind who are like, oh yeah, we probably do. Like if you just think about it pretty deeply and think about probability, it's more likely that we are living in a civilization that's within another one or layered even further down. Is the many worlds approach not able to actually does it kind of uh front with or sort of oppose the simulation argument, or do you think they're both compatible in some capacity?
That's a really interesting question. I'd like to think any interpretation of quantum mechanics is compatible because
Okay.
really it's just telling us what's going on in our simulation. And
Mm.
the programmers of our simulation can choose quantum mechanics to probably work in a bunch of different ways. Um, and that would all be fine with the programmers. So I think uh, if the programmers of our simulation wanted to say, okay, there's an infinite number of parallel universes that we're programming,
Hmm.
and this is how collapse works. This is how collapse of superposition works. Is the world split every time and you get every option? Well, that seems fine.
God, what a stubborn worldview, or even just difficult to hold on to, like personally, worldview of we're not only one of an infinite number of universes, but we're also one of the infinite number of universes where you happen not to be real. It's just that
Right.
layer. It would multiply the already infinite amount of computing power that'd be necessary for the universe to exist and even run one universe. It would multiply infinity by infinity once more, which
Right.
would be absolutely incredible. Um, that's so funny. So what to bring it back to Bell's theorem? What are some of the what did Bell have to say specifically about the hidden variables, and specifically like why they weren't applicable? Because you said that he kind of discounted them, said no, local hidden variables can't be. But what was his opinion again on universal hidden variables and the fact that there might be some hidden essence or hidden aspects of subatomic particles that we're not aware of that do influence how they interact?
Right. So it's I mean, before I even answer your question, a sort of meta
Uh-huh.
point is that a lot of these theorems, a lot of these results in quantum mechanics are actually just pieces of math. And then it's
Okay.
up to a lot of people looking at that pieces of math to actually recognize what it is they're saying about the universe. And so Bell himself like didn't have any opinions on global hidden variables or local hidden
Gotcha.
variables. He just published these like three equations and said this is what must be true. And then since then, it's been interpreted and misinterpreted in various different ways. But the quote unquote correct
Mm-hmm.
understanding of Bell's theorem as we know it now is that it forbids local hidden variable theories and it says nothing about global hidden variable theories. So
Okay.
Bohmian mechanics, which probably we'll get to shortly, is an example of a global hidden variable theory. And lots of people like to discount what is actually a really nice interpretation of quantum mechanics because they just
Mm-hmm.
hear the phrase hidden variables and they're like, oh, Bell outlawed that. We can't have that.
No,
But
yeah,
actually,
when reality, like the what his theorem is actually interpreted as saying is that it's not hidden variables, which is the thing that can't be. It's just a specific type of hidden
that's
variables.
exactly right. That's exactly
Gotcha.
right. Yeah.
Oh, that's really interesting. So when it comes to the actual process of how these theorems are kind of created, um, it's usually, I mean, it's based off the fundamental math first, and then like a series of different interpretations. So for example, like Bell's theorem, are there multiple different interpretations of Bell's theorem, or is there one interpretation that people can say this is roughly the correct one?
Right. So this is this is a really hard question because it gets at sort of what is scientific consensus? Like how
Yeah,
do we know when we actually have a scientific theorem instead of just a bunch of scientists being fooled about something or being wrong about something? And
collectively.
so there's right, and it happens. It definitely happens. And even there are divides between like philosophers of physics and physicists themselves on what these different pieces of math should be saying.
Hmm.
And so the I guess yeah. What exactly was your
Well,
question?
because it seems to me that it's regardless of your opinion of math, if it's something that's man-made or sort of embedded in the universal structure, right? Um, it is in some way more objective than interpretation, right? It's some in some way more objective than narrative structures that we use to describe everything.
Right.
Um, Math in some way has this sort of functionality to it that makes it just applicable and without really a need for an interpretation for it to then be able to discover more things, which is the predicament we're in with these interpretations is we have these brilliant physicists who are coming up with these great outlines of here's what's true,
Right.
and then it requires a series of discussions and interpretations, and then hashing out those interpretations, which are much more open to either bias, or cognitive biases that are inbuilt, or even discussional preferences, or all these different aspects that kind of influence the creation of bad ideas overall. So I think my question is
Absolutely.
like,
Yeah.
is it seems like there has to at least be some different tribes that kind of grow out of groups of physicists where they fundamentally disagree on what actual theorems or what specific theorems mean, which is, it's better than some other areas in science where they'll like dispute the actual evidence itself. But it seems like physicists are on the same page and say, oh no, this is true, but here's actually what it means, because the thing is it's not valuable if it's not valuable on its own. Knowing that it is true is not enough in this case, um and it requires that interpretation. So it seems like there has to be a disjunct between different physicists with that, right?
Right, definitely. And for Bell's theorem in particular, I'll put it everyone who reads Bell's original paper can understand that it's only talking about local hidden variables. But what
Mm.
happens is very few people go back and actually read a 30-page dense technical paper. And so there can be
I wonder
even
why.
right, no, I wonder why. Even within the physics community, there are lots of people who still think that it says something that it doesn't, mostly because they just haven't gone in and actually read it. And there's this common myth among physicists that it forbids all interpretations of quantum mechanics with hidden variables. Hidden variables are very taboo. And
Mm.
so when Bell came out and he had this interpretation that some people could misinterpret as saying, well, actually everything that has hidden variables is gone. Well, that made a lot of people very happy, even though they were wrong. They were using the information incorrectly.
Again, the bias, it follows everywhere, unfortunately, except in math, which is the tricky part here, right? That adds
Oh,
another layer of friction.
right.
And then, so you mentioned Bohmian. Is that how it's pronounced? Is
Yeah,
it?
Bohmian mechanics. It's
Okay.
named after a guy named Bohm. Has nothing to do with Bohemia.
I
Yeah.
the computer kept auto correcting Bohemian. I was like, no, not this time. Um, so how does it differ from Bell's theorem in the many worlds interpretation?
Yeah, so well, okay, just to be clear, Bell's theorem is a result that talks about like the limitations on other interpretations of quantum mechanics.
Okay, okay. So it's not
And
actually an interpretation on its own. It's
right.
just saying here are the rules that other ones have to be guided
That's
by.
exactly right. That's exactly
Gotcha,
right.
gotcha.
Yeah. And it's
That makes sense.
it's definitely the most famous and probably most powerful of those sorts of results. And whereas the many worlds interpretation itself, oh, did I cut out there? My screen
No,
froze.
oh no, you're still live on this side.
Okay, great. We'll cut that out. The many worlds interpretation itself is indeed an interpretation of quantum mechanics. It tells us what quantum mechanics should say about the world. And Bohmian mechanics is in the same boat. It's the same type of thing.
Mm,
So what Bohmian mechanics does is says it has this pretty out there idea, I guess you could say, and it says that all particles are fundamentally pushed by what's called a guiding wave. So there's this sort of magical wave pushing particles around. And when superposition happens, it's actually not a superposition of the particles that we can end up observing. It's a superposition of the corresponding waves that are behind them that we don't interact with. And so, in this sense, everything that we care about, like all the physical stuff, so all of the
mhm.
particles, do actually have definite positions, definite momenta. You know, like I know whether a particle is here or there in Bohmian mechanics. That's a legitimate question. It's one or the other. Um, and the superposition, this weird stuff going on behind the scenes, is kept to behind the scenes with these guiding waves. And depending on how the superposition works, the waves will either sort of interact or destructively interfere with each other to change where those particles are pushed in the future.
So it's akin to a ship on the ocean being pushed to a different position, but we don't see the actual currents underneath the water that are
That's
guiding it there.
exactly right. That's
And
exactly.
there and there's no way for us to measure those waves currently. Or has there been? Do you know if there's been any evidence of our ability to actually interact with or in some way observe those waves apart from just what they're doing?
Right. So it's unclear, like the creators of Bowman mechanics
Hmm.
don't actually say whether or not these waves are quote unquote real. So for a lot of things in physics, when we talk about a wave or when we talk about, even particles sometimes,
Hmm.
like it's not clear whether or not these are mathematical like effects, like we can just associate a piece of math to this
Hmm.
point in space, or whether there's something there, like something fundamentally there outside of just how we would be interacting with it. And I mean, even whether or not like something fundamentally being there is a legitimate question, like it is contentious because you could say, oh, well, how stuff itself, like how we know stuff exists is by
Hmm.
interacting with it anyway. So it's sort of meaningless to say, well, stuff is already there. Like what the like who cares whether or not this is like a fundamental like wave, right? Like what
Hmm.
does it even mean for this wave to be real if the only way it interacts with stuff is by pushing it around? So it's sort of one could say it's not a good question to ask whether or not we've measured these waves because
Hmm.
it's sort of like, well, we've seen what particles do, and what
Hmm.
particles do exactly matches the behavior of these waves that we can describe. So maybe that's just good enough to say that the waves are real.
But that's the thing is it doesn't seem good enough to actually explain the whole picture of what's going on in our universe, right? And I think that's the difficult thing for me to wrap my head around right now is we're hitting a barrier, it seems like right now with quantum mechanics that isn't matched in other areas of science or even other areas of physics, right? It's akin to the dark matter issue of what the hell is going on there. We have this mathematical evidence of this dark matter being here and being a good portion of the universe, what, like 80 and 90%, um even higher. uh
Dark energy, yeah, yeah.
it's dark energy.
Yeah.
So we know it has to be there mathematically, but obviously because of the name and other factors, we can't directly observe it in any meaningful way, um, apart from its influences on other things. And I think there's just this like tenacity, or this need to actually be able to directly observe the things that we know have an effect on the world around it.
Well, I think
Um,
this is a really interesting question because why do you think we directly observe anything? Like if
yeah.
you say I have like some really interesting substrate, like I'm a biology concentrator working in one of Brown's labs. I look under my microscope. I think I see this substrate,
Mhm.
right? Like I think I can say like, oh, this biological thing is really there. But all I know for sure is that when I look through a microscope, there are photons like getting
Mhm.
reflected off of this thing and
Yeah.
then bouncing back into the microscope and then bouncing into my eye. And
Mhm.
so whether or not like it's technically possible, right? It's technically possible that there's nothing there. There's just nothing beneath the microscope, but
Mhm.
the microscope knows when I look into it and I expect to be seeing this piece of biology that it
Mhm.
should emit light into my eye, right? Like
Mhm.
it's actually totally impossible for us to outrule that possibility.
Yeah, and
And so
it's the classic cognitive barrier, right? We only know what is currently existing in our brain through our senses, through those slits, in a very, very similar way to the double slit experiment, where we can't actually tell until we look at it and are just trusting the world and just trusting our instruments to actually be guiding us towards truth. And that's the thing is the only real proof of that. And it's not proof of whether or not there's some the mind the vat experiment or situation. It's not proof that there isn't some deity or some super powerful god or tyrannical dictator who is manipulating our brain and actually causing us to have sensations or experience things that aren't there. But it is at least proof that within that context, within whatever we're experiencing, there is utility, right? So knowledge in capacity insofar as it has a functionality and it has a proven functionality to it, I think is a test of whether or not we're observing something actually, for us, actually occurring, right? And because of that, the math seems to need, like, it has to be enough, right? By those same parameters that you're just talking about that apply to every other object that we experience day in and day out. It's essentially the same thing, just slightly less diluted, or sorry, slightly more diluted than what we're experiencing with the waves in the Bohmian mechanics model, right? It's the same thing. We don't actually have the proof there. We just kind of have knowledge of it doing something. Um, and then the mechanics actually allow us to have utility in context of quantum mechanics and allows us to discover more things and understand it in some different way, right? It seems to fit the picture. And I think because
right.
of that, I think you're right in saying that there isn't any. It's not necessarily a good question to ask. Can we directly observe it, right? Because we're observing it as well as we can essentially observe anything, which is not observing it.
Right, right. No, exactly. And I think this is like a really interesting point that quantum mechanics is the first theory that, seemingly put the observer or put observation or put
Hmm.
knowledge or put even like, is there a fact of the matter of what these particles are doing? Is there a fact of the matter of what exists? It put those
Mm.
questions at the forefront of physics, which is crazy. No one had any concerns before the 1920s about whether or not there was stuff there, right? I look around me. Of course, there's stuff here. Like that's, that was left to tables, at philosophy discussion conferences.
Yeah.
Like that wasn't real, right? No, no offense to philosophers, but certainly quantum mechanics is the sort of thing that brought it into the broader scientific community and broader societal community,
Mm.
like to actually be asking these questions of, well, what effects does the observer have on the system you're observing? Like, is there any way of objectively knowing what's out there? All of these really interesting, crazy questions are suddenly like in your face when you try and say anything about quantum mechanics.
It sounds like quantum mechanics is the thing that brought the keen physicist to the philosopher instead of vice versa, right?
Right.
Which is, I think that's a testament to the actual implications of the field and really the importance of trying to understand it. Where typically, oftentimes in philosophy, it seems like there are scientific ideas that are taken um, uh, sometimes out of context or sometimes not, and applied, in context of larger philosophical context. Oftentimes it's not the opposite. Oftentimes it isn't the philosophy being needed to understand the physics. It's the other way around. And I think that is a really great testament to the actual importance, right? And then the last of the four, before we move on to the really fun fifth one, is the Copenhagen interpretation. Can you give us a brief breakdown of that?
Yeah, so the Copenhagen interpretation is essentially and unfortunately the most popular interpretation of quantum mechanics right now amongst physicists. And more or less what the Copenhagen interpretation says is it says that these sorts of questions that I was just asking are essentially unanswerable questions. So what's going on behind the scenes when we have a superposition of two, quote unquote, incompatible states? Well, we don't know. Like we can't measure it, or there is no fact of the matter. It just says like, there's nothing going on, and things only actually sort of exist. Like a particle only maybe exists or has a location after we measure it. And that's what Copenhagen interpretation is saying. It comes along with this famous phrase, "Shut up and calculate," uh, regarding regarding how much you should be thinking about what's going on behind the scenes.
And then what the heck? This is easily the weirdest one so far. This is crazy.
Yeah.
Um, and to give it a little bit more context of when and why it was created, I read of the Wunderkinder, the Wonder Children from Bohr.
Yes,
Can
exactly.
you explain that backstory a little bit? What was actually going on when it was created? It was
Sure.
20-year-olds who helped come up with this.
Right. So Bohr in the 1920s, 1930s is probably one of the most influential physicists alive. He's has a strong personality. He has a large following. He works really well with other physicists, and so he has this large group of disciples, and he teaches them his idea, which is the Copenhagen interpretation. And
That's ridiculous.
yeah, and he's so convinced. He's very convinced about the metaphysical implications of the Copenhagen interpretation. Things like, well, it's not there until we measure it. Things like that. So the moon wouldn't be there if we're not looking. If the moon were a quantum system, I mean, but yeah. So this very strong figure in
Hmm.
physics comes up with this idea that's pretty bad. It's pretty bad if you care about the really understanding our world more
Mm.
than just making accurate predictions. Like if we want to understand like why we're making accurate predictions or what's going on behind the scenes or potentially how to combine quantum mechanics with other theories, which is like there's billions of dollars going into that sort of research right now. Copenhagen interpretation is not so useful. It doesn't let you do those things because it doesn't provide a backstory of what's going on. But it became incredibly popular almost purely because of the sociology of the physics community. There was influential figures who taught what would be his influential disciples, and they carried on his legacy to promote the Copenhagen interpretation.
Oh wow! So one of the larger blunders in quantum mechanics, right there. People falling prey to the age-old problem of tribalism. That's
Yeah, no, it's
damn. I
true.
thought physicists would be better. I thought they could escape the trap. God, um, that's fascinating that it took so long. So how many decades until it started to get moved away from? Because you mentioned the other ones, the many worlds interpretation was 50s,
Yeah,
and the Bell's theorem, which I mean was just gave context. The rest of them was 60s.
right, right.
Um, so like how long
Well,
until the
right.
established scientific community actually started saying, all right, maybe we should actually leave the Wunderkinder away,
No,
and Bohr
exactly.
as a whole.
What's actually incredible? So Bohm, who created Bohmian mechanics, he
Mhm.
did that in the late 1940s. But what's really unfortunate about his story is that he was a staunch communist. And this was just as McCarthyism was rising. He was trying to do physics in the United States.
Oh
So
no.
this incredible guy who's about to save us from the Copenhagen interpretation, maybe
Mhm.
after only like a decade or two, let's maybe not too bad. Ends up getting expelled from the country, moves to Brazil in hiding, and can't go to any conference, can't communicate with the top physicists, can't promote his ideas, despite having found what's a really, really good alternative to the Copenhagen interpretation. And that just set physics back so many decades. So his idea didn't get rediscovered for numerous decades after that. And it never had the chance to sort of fight against the Copenhagen interpretation when all the original founders of quantum mechanics were there, because he's stuck as a communist in Brazil. So even
God,
these,
talk about
it's
holy
like a bunch of
crap.
sociological matters, a bunch of political matters getting so much in the way of having the right sort of ideas when it comes to quantum mechanics. It's crazy.
It's crazy that because I think it goes both ways for physics generally. Like obviously, a lot of nuclear physics is directly the product of the State Department in World War II having a military interest in furthering it, right? And no doubt that's the same for like a lot of aeronautical sciences. Which unfortunately caused the U.S. to recruit a whole lot of Nazis after World War II, and a bunch of other sciences which have equally been sociologically further, or sorry, because of sociological reasons, have been furthered in really meaningful ways. But it seems like this blunder is on close to on par with some of the other big tragedies of knowledge and history, like I don't know, the Library of Alexandria burning down from some military accident, to that one random monk who accidentally erased calculus to write a Bible translation over. Like these massive blunders of sociological and sort of larger political structure influences on science. I didn't realize they extended so intimately into the quantum realm.
No, absolutely. And I think had it not been for all of these really human factors influencing
Yeah.
how physicists think about quantum mechanics, the Copenhagen interpretation never would have survived past like the 1940s. But instead, it still has the plurality of physicists, quote unquote, ascribing themselves to it, even though really what these physicists do is they don't think about what's actually going on behind the scenes. They're perfectly happy to shut up and calculate. Uh, and so, yeah, it's I mean, only like really the tide has started turning over the last 20 years or so. 20 to 30 years is only when people started realizing we need to be doing something different with quantum foundations. And here are all these good alternatives to the Copenhagen interpretation.
Is one of the good alternatives the GRW that you mentioned a little bit before? I know nothing about it. Can you flesh that out?
Definitely. So how the GRW interpretation works is that it actually removes the special place of the observer or the measurer from quantum mechanics. So normally you have superposition, and the superposition will collapse when there's, a quote unquote observer or measurer
Mm.
interacting with that superposition, and then it goes back into one of its normal sort of states, either to the left or to the right instead of superposition of left and right. But what GRW says is not only does that collapse not occur, collapses just occur randomly. It's like every 10 to the negative 27 seconds, there's a collapse of every single superposition in the universe. And
Wait, is
this,
that the standard interval between collapses, or is it like actually just a random amount of time between collapses?
well, right. It's a random
Okay,
amount of time
okay,
between
gotcha.
collapses. And this is, yeah. Um, and then Yeah, exactly, exactly. So the problem is a lot of people who look at the Copenhagen interpretation, they say like, okay, well, we're the ones interacting with this electron, right?
Mm.
And so, okay, so that's what makes it go from a superposition of left and right to either left or right. But why are we special? Like what's special is actually going on there? Is it the fact that we're human? Is it the fact that like we have physics PhDs? Like suddenly we get this like, like special role about changing how electrons work? Because
Mm.
electrons at every single moment are interacting with other things. Like there's gravitational waves passing by, there's photons, there's whatever. But still electrons are in this superposition, right? So it's not just any interaction that will collapse the superposition into a normal sort of state. It's something weird. It's something very weird going on. And it's hard to say, like, some people even want to say it has to do with consciousness, which is an interesting option. But essentially, how GRW reframes it is that it just has to do, and this is different. This is actually different math. This is observably different math than
Mm.
standard quantum mechanics. It says that it just has to do with how many particles are in the total system. So when I observe a superposition, suddenly that's a very large number of particles in that system, like
Hmm.
um, which causes like the probability of collapse of that system to be very, very high. And so that's how they get around the fact that whenever we see humans interacting with the superposition, it is a normal state. But when there's just like two small particles going on, there isn't a collapse.
Oh, that's fascinating. So it's directly, man, how would that change the sort of the quantum mechanics underlying larger bodies of matter? You know, like if I have a bowling ball, how is that going to be different than a basketball that has a perfect vacuum or something? Like what is the um in addition to conscious entities who are made of matter, unfortunately sometimes, um, how does influencing the quantum realm, that capacity, does that also mean that high density objects, um, at least on a quantum level, um, are different fundamentally in how they kind of play out versus if you just have two particles, a certain distance away in a perfect vacuum? Is that what that would mean?
Well, so actually, it in some sense it almost means the opposite,
Really?
because
Okay.
what the Copenhagen interpretation does for
Mhm.
contrast is it says, well, there are these things called like classical bodies. Like who knows what those are? That isn't well defined. And it says when those classical bodies or classical objects, which presumably I am, like interact with these electrons, that's when a collapse will occur. Whereas GRW actually says that everything is treated equally. There isn't a distinction between, classical bodies and quantum bodies, or classical states and quantum states. Actually, I'm also a quantum state of a ton of particles, and it just so
Mhm.
like I seem like I'm classical, like I seem compatible with physics pre-quantum mechanics because I have so many particles in me. And
Mhm.
if we reduce the number of particles in me, I would slowly move from seeming classical to seeming quantum, even though the entire time I really am a quantum system.
Oh, that's fascinating. Which is again, the GRW model seems much more in line with other ways of classically understanding the universe. I mean, specifically material, and sort of Newtonian. That's fascinating. That has a direct correlation potentially to the amount of stuff around other stuff. Um, is that one of the approaches that you personally are more on board with, or out of the five now, which one do you think beckons you the most?
Uh, I'm probably biased towards Bohmian mechanics.
Nice.
Between yeah, I like this idea of global hidden variables. It seems like it seems good to have a sort of locality. It seems good to have determinism
Mm.
because GRW and Copenhagen both don't have determinism, which
Oh, okay.
makes right, because GRW has the random collapses, random periods between individual collapses, and
Okay, gotcha.
Copenhagen has the random choice, yeah, random like normal sort of collapse of superpositions. Um, and
Mm,
so Bohmian mechanics is deterministic, which
gotcha.
seems very nice. And it has bonus side effects that I didn't even mention, such as being compatible with special relativity, uh, which is one of these big litmus tests for how far a theory is going to make it in physics.
Why is that?
Why is it a litmus test?
Yeah, yeah.
Uh, well, so special relativity. We should just explain the entire history of physics today. Um, Special relativity is this idea Einstein came up with also in the beginning of the 1900s
Hmm.
uh, that essentially says things like space-time is connected. So space and time form a unified four-dimensional space. And if you're moving faster, things around you get shrunk and including time. So space gets shrunk and sort of the time around you gets shrunk. So you
Hmm.
could experience less time the faster you move. So there's this theory, which isn't talking about quantum objects, but the idea is that if it's compatible with how it treats like this time and space, this big idea of time and space, then like there's sort of hope for a bigger, better theory that makes everything compatible. Because how physics generally works right now is we have really small stuff, which is the quantum realm, and we have really big stuff, which is controlled by or described by relativity. And we, as of yet, have no way of combining these two scopes. We want one theory that decides all of physics, and it doesn't exist. It doesn't exist at all, as far as we know, as far as we've found. And so there's two. So you at least want to be compatible with a little bit of relativity called special relativity, in order for there to be a hope that it'll end up being the ultimate equation that tells us how the universe works.
So the Bohmian mechanics actually gives us the best chance out of the five to have some compatibility and create a theory of everything.
I mean, so to be fair, the Copenhagen interpretation also does that. It
But we've
just
established why it's trash
right.
so
It
far.
just doesn't tell us anything. It doesn't tell us about what's there. It yeah. It leaves its hands in the air and says, I don't know, which isn't really useful for people who want to think about how the universe works.
Which probably
Saying
makes it compatible for a lot of bullshit physics too, I'm
right,
sure, right?
right. No,
It's
exactly.
compatible with a ton of also just very inaccurate conceptions of the universe as well. It
Right.
opens itself up because of its ignorance
Much
to a
harder to be
lot of
wrong when
things.
you don't give an answer. Yeah.
Exactly, right? And much easier to be interpreted by a ton of people who don't actually know what's going on.
That's right.
Um, so next in this quest to understand what is going on in the smallest realm possible, um, how sorry, hold on, let me jot down what time this is happening at. I keep like trying to transition, not going. 49 transition. Um okay, and so we're gonna transition into questions on part three. All right. So this is a little bit different from the past discussion that we were just having. Um, we're going to transition more to how these theories are interpreted, or probably much more common, misinterpreted. So I was going to ask you, how do you see these things in quantum mechanics generally getting interpreted in pop culture and in media?
Definitely. I mean, there's a whole host of different ideas. Sort of quantum science fiction has become its own genre in and of itself. You almost append the word quantum in front of any sort of technology you want to exist, and your readers just sort of believe that maybe that's how that might work. But very common ideas are things like we're all connected as consciousnesses because of the way, maybe either because of superposition or because of the way the observer plays a special role in quantum mechanics. And that comes out of nowhere. It's sort of maybe if formalized correctly, it could be like a sort of different version of the many worlds interpretation. There's this thing called the many minds interpretation, where actually the only splitting of different worlds is, or the only thing that splits between the different worlds is actually the consciousnesses. But I'm pretty sure that's not what most writers are referring to. And so, right, so we have this whole idea, like most likely consciousness just doesn't play a special role in quantum mechanics. Um, there's, I suppose, no good reason to believe that it should.
Why I think there's one good reason why it might seem like that it should, which is the classic like ego and confidence of mankind to want to involve the one special thing we have, our consciousness, in everything we can. It typically is the number one focus of all spiritual practices, right? It's trying to figure out the significance of this thing that we're always embedded in and that we are. So because of that, it's understandable why pop culture has this weird fascination with quantum mechanics and consciousness. Um, so if that is not one of the implications, what are some of the more interesting implications then? What are some of the places that do have genuine places of curiosity, that are science fictiony, that
Right.
do actually have pertinence to it? You mentioned teleportation,
Yes.
and the I think we covered why people say the moon might not be there when you're looking at
Right.
it. And then the parallel worlds we've already covered. Um, and the connected humans. I think we've answered that as well. But I want to get to the bottom of the teleportation because I understand that the quantum entanglement is a thing that has been observed and is known.
Definitely.
Um, so tell us a little bit more about that.
Yeah, so there's almost two different effects here. One is called quantum tunneling. And so what happens is uh, there's this other phenomenon in quantum mechanics that we haven't even talked about yet, which is particles end up acting like waves and vice versa. It's called this wave particle duality. And
Oh.
so if I have what I think is just a thing right here, okay,
Hmm.
inside of this box, well, inside of this box like this, it's below the top of the box. Well, normally things don't just like hop over and out of boxes, like they just stay where they are. But because when a particle isn't being observed, when it isn't interacting with this large scale system, it can go into sort of these superposition of states. It can act like a wave. So a particle just in a box can end up having its possible locations spread out. So the particle, my electron that was actually in my box, can have its possibilities for when I observe it end up being outside of that box. So you can have, which is crazy, which is really crazy. This
Hmm.
is a real thing. We've tested this well. So you just put a particle in a box. You let it sit there for some amount of time, and then you try and measure it. And sometimes it'll appear out of that box. And this is called quantum tunneling because it literally lets you tunnel through walls.
Wow, that's fascinating. I feel like that example is immediately ruined if the object you're talking about is a frog. I think is the only big issue. But
Well, it's not clear. Technically, frogs can also tunnel through walls. It's just the odds are much, much lower.
um, that would be that's the demonstration I want with quantum mechanics. I hope by the end of
Sure.
our lives it gets to a point where we're able to move little froggy
Yeah.
guys, through
You
through
you put a
quantum.
trillion frogs in a box, I'll make it happen.
Okay, perfect. I That is gonna be a fun task. Frog World is the only way to get there. Um, which is Elon Musk's newest venture. Instead of trying to make Mars habitable for humans, he just wants it to be Frog World to be able to test this theory. Um, okay, so that's teleportation. I want to know more about the entanglement of particles. The classic. I guess it's the opposite of classic. The very new and cutting edge and novel idea of being able to have pairs of particles that are somehow connected in a way where if you move one, the other one moves in a mirrored way. Is that in line with what is known currently in quantum mechanics?
Yeah, I think you could put it like that. Essentially, the actual technicalities of how it works is that when you have these two particles in what are called an entangled state, as soon as you observe one, as soon as you collapse whatever superposition it was in and figure out what its state is, it could have been like in a superposition of being to my left and being to my right, right? Something like this. And then if it chooses left, well, the other particle will choose the exact same thing instantaneously.
Oh, that's fascinating.
So by interacting with something over here, I can have something a million miles away. And as soon as I see that the thing here is to the left, I immediately know what's going on with that other particle a million miles away.
And it has that, I mean, it has to have been proven by the math first, but has that been observed as a
Yeah,
legitimate thing?
actually, pretty recently, just in the last 10 years, we got devices sensitive enough. We had a cross-continental test, which is pretty much the largest distances we can manage as a species right now, to show that actually it is this instantaneous phenomenon, and it's not just propagating at the speed of light. But yeah, we've tested it. I think we've used electrons. We've almost gotten to the point of having entire hydrogen atoms. Entangled with each other. So it's maybe one day we'll have entire frogs, say, entangled, and you can right exactly. You can determine crazy information about very far away frogs by the frog you have right there.
Well, I mean, the really, I feel like significant impact there is the ability to communicate over distances greater than like a light year. We could potentially have two particles that are entangle in such a way. If we have an entire like atom be able to move, it wouldn't be too difficult to make a trigger system for that, right? Where you move one and then bam, a light year away, your buddy gets the alert that the intergalactic space force of frogs that we should not have given intelligence to on Mars. That was a terrible idea. It turns out that they're coming for you. I think that sort of communication system does really change prospects for like the implications, the actual like technological advantages of quantum of
Well,
quantum
so
computing.
I don't mean to ruin your dreams here,
Oh
but
no, you're not
the
telling me it's no.
right. So the unfortunate fact of the matter is
Uh,
it's actually been shown to be impossible to transmit quote unquote new information. So you can't right. So all we have the option to do with these
mhm.
entangled particles is make them collapse out of an already like pre-existing superposition of states. So the only sort of information that you can actually tell to your partner on a different planet, trying to coordinate the interplanetary defense system, uh,
Uh-huh.
it is, I mean, yeah, you can't like the only thing you can tell him is the sort of stuff you set up originally when you started with those two particles together and you like put them into a superposition. So
Oh,
the
that's so
information had to
interesting.
have been there the entire time, because information going faster than the speed of light is a big no-no.
Oh, damn. I thought there was one way out. Okay. Well,
Right,
that's
right.
unfortunate. That doesn't quite have the same significance
No,
when it
exactly.
comes to the actual advantages. And I feel like I want to know your personal opinion when it comes to kind of the one of the things that when I think quantum mechanics, I this is definitely the first topic that comes to mind is the idea of quantum computing. Why is it quantum? Is it just a tagline that they threw in there for good marketing? What's up with that? Tell me a little bit about how it's actual quantum mechanics and based off quantum mechanics.
Right. So it's based off of quantum mechanics because precisely because we have these superpositions of states.
Hmm.
So instead of normally, say in a computer, you have a gate, you have transistors, you have gates, and either there's electricity flowing through the gate or there isn't, and this is a one or a zero. Um, and so instead of having that sort of classical one or zero, this is not technically correct, but loosely how quantum computers work is that you get superpositions of one and zero. So there's a lot more combinations you can do, and it's much more powerful than just say adding a third option. Like it's not like you have like three different colors of electricity flow. Like you're
Mhm.
adding a third option. Like the fact that it's a superposition and quantum mechanics has these essentially strange bits of math that say how superpositions evolve and can collapse allows you to get a lot more powerful computation.
Wow. And so it will increase the further range of our computational abilities if we can do it. Now, why and this might be too technical of a question when it comes to quantum mechanics for quantum computing. Why is it that the systems have to be kept so cold? Is it to stop particles from moving or having any additional energy? Is that really the reason?
Yeah, that's pretty much exactly it. These systems are very fragile, and if one of these superpositions collapses when you don't want it to, your entire computation can be messed up. So
Oh,
yeah,
God.
exactly. Keeping things cold, um, yeah, it exactly prevents things from moving.
And it seems to be one of the largest difficulties right now in quantum computing is how do we keep these things near or as close to absolute zero as we can get, right?
Yeah, I mean, keeping them isolated is a really big difficulty, and
Hmm.
having everything coordinated. So right now, I mean, probably my information is a bit out of date, but we have quantum computers that have 50 qubits or so. Qubit meaning quantum bit, 50. So if you compare that to the processor on your computer, which has billions or trillions of bits, right? We're lagging pretty darn far behind. Uh, Precisely because all of these very tricky limitations of not being
Hmm.
able to interact with the outside world, having to be very cold, having to have this, quantum like cohesiveness to actually make use of the operation is very difficult to scale.
Well, once again changing focus because we're about out of time. But I really just want to know, in your opinion, what do you think is next for quantum mechanics? When it comes to interpretations that are going to live on, it seems like the Bohmian mechanics model is probably going to stick around for a while. But when it comes to like what the next frontier of the entire field is, what are you hoping to expect next when it comes to answers
Well,
or
I'm a simple
questions?
man. I have a simple question. What's going on? That's all I really want to know. I'd love if someone could just paint a cohesive picture of the entire universe, and say what's going on behind the scenes and why everything acts the way it does. I'd be totally satisfied with that. I don't need much more.
Any further readings for the audience or for me?
Absolutely. I mean, people who are interested in this sort of thing
Mm.
should read the author Tim Maudlin, David Albert. Adam Becker had a really recent book that I thought was great called What is Real? Very, very topical about the history of quantum mechanics. There's experiments like the twin slit experiment. Um, yeah, overall, there's a lot of really interesting resources out there regarding quantum mechanics and what it means for our reality. And I think anyone who's interested is going to have a good time.
And then on that last point right there, if there's one big takeaway from all the time that you spent studying quantum mechanics thus far, what is it? What's the solid piece of knowledge that you might take into your own life? Or because it's quantum mechanics, probabilistic piece of knowledge that you might take.
Right, exactly. So I will actually answer with two. I would say first is that physics is incredibly human as a process, which actually surprised me a ton when I learned about the history of these theorems and why they haven't taken off. There's a lot of political, a lot of sociological, a lot of economic reasons that actually get in the way of us finding the right theories about the universe,
Hmm.
which one would hope physics is insulated from, but ultimately it's a human endeavor and it is not. So I think it's important to stay vigilant about those sorts of things for physicists and as a general public. Not, of course, to trust scientists because scientists are generally very correct, but also do some critical thinking on your own about how people could be wrong or what other factors are going into play.
Hmm.
And then the other is that, uh, I mean, quantum mechanics is just an incredible world. The notion that there could be, I mean, you just get to choose. You get to say, well, I think things should be random, or I think things should be decided by the stuff around me, or I think here's how causal chains work. And there's compatible ways of thinking about how the universe evolves and compatible ways of thinking about physics that let you incorporate these really awesome metaphysical ideas. And so I think it'll just be crazy when one day we have a decision about which one of these is right, and it tells us a lot about the way our universe will evolve.
And no doubt, those big metaphysical questions that are embedded in the entire study is probably one of the reasons why it's picked up as such a pop culture phenomena, right? It's
Absolutely.
why the writers use the now literary trope of quantum tech. Um, and I think it also speaks to the deeper actual legitimate questions that are lying there underneath. Regardless of how much it's bastardized or misinterpreted or used from some very illustrious and oftentimes kind of annoying authors online to further ideas that aren't actually based in science and that they want to find some strange proof for. The reason why they're able to do it so easily and why it's such a common practice is because there is actually something there, something that does actually
Yeah.
shift how we look at the world, and isn't in some ways is much more complex and less intuitive than we can have ever expected. In some other ways, and with some other approaches, is much more intuitive.
Right.
Um, and I think that's a more novel, more mature way to actually look at quantum mechanics. Because all too often it's just seen as this thing that A is difficult to understand, which is right, but B is fair game for speculation and poor kind of bastardized interpretation. So I appreciate talking to you today. No doubt this is thoroughly demonstrated why you're the science writer and advisor for the website. No doubt that you've really flexed your skills today and knowledge. So I thank you very, very much for A, coming on, and B, enlightening me a little bit. So thank you.
Yeah, thank you.
All right, I'll talk to you later.